Welcome back, Ib Gang, to another episode of
It seems today that all you see is violence and movies and movies on
But where are
TV.
those good old-fashioned values? And cry and cry.
So I don't really know what this is. I don't know what to do with this whole thing, or what not to do with this whole thing. So really, so basically, really, my whole entire project was based off of the idea of faster than light travel, and hold on. Okay, that's better. Okay, so my whole IA was based around faster than light travel. But there's a problem with faster than light travel in, like, typical means of propulsion. And, like, acceleration with, like, a car or a plane or a thingy, you know, like one of those. And it's because, it's because when you have a, object or like a set of normal matter, and you try to just accelerate it using like a jet engine or something, the amount of energy you have to put in to the object to make it go certain speeds is infinite. And so, okay, that was poorly phrased.
Values on which we used to rely.
Okay, so basically, as an object increases in speed, it increases in mass as well, but it's not really, it more increases in energy. It more increases in like kinetic energy as it's moving faster, and it's more of a kind of inertial mass. Is when you get up to the speed of light, an object with mass technically would have infinite mass at that point because of its inertia and that kinetic energy pushing it in that direction, which would make it basically infinitely impossible to stop as well. It'd be really strange, and that's why it requires infinite energy to reach those masses once. Okay, so you have a thing, you accelerate it, and then if you want to accelerate it more, it has more mass, so you have to go further down. No, stop it. I can see you. I can see your arm. Hello. Okay, so really you just need...
Who are you talking to?
My class. Okay, so you have an object and you accelerate it, and once you accelerate it, that object technically has more mass, so it requires more energy to accelerate, and that just keeps on going up kind of exponentially until you get to the speed of light, in which case it would require an infinite amount of energy to accelerate it to that point, because you just need more and more energy over time. And that's why we can't accelerate things to the speed of light using normal means of propulsion and everything. And that's why something like the warp drive was theorized, of course, based off of Star Trek, but now NASA's kind of looking into it in a different way. But yeah, so basically, in my math IA, I had the UU ship, as you all saw in the last video. And this ship was really cool because it had this device, and this was before I wrote the IA, so I changed it up a little bit. But basically, here, I'll redraw the ship. Okay, so in the last video, I had a spaceship that looked like this. right? And I had a little device here that would be like whoop, you know? No, 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 you don't want that. What you want is a device in the ship, in the middle of the ship somewhere, and it would be like whoop, and it would create two things. It'd create a black hole on this side and the front of the ship, wherever you want the ship to go, but it would be the perpetual black hole. And then on this side, it would instead be a white hole, pretty much. This object would be the same as the black hole in many ways, but instead of pulling the ship towards it, it would push the ship away from it. And this would cause just even more acceleration. It would basically make it, here's the ship, and it would be going this way because of the black hole over here, but then this would also make it go this way because it has negative mass. When I have negative mass, it pushes it away instead of pulling it away because of how mass works. It would be like, here's the ship again. It's riding on a wave, and this is the black hole. It goes down like that, so it's rolling downhill. But the white hole would basically, this is like no mass. Oh wait, sorry, it has a little bit of mass. This would be like no mass right here, you know, just normal space. But then with the white hole, it'd be like a hill. Quick side note here, basically it would be rolling down infinitely. Sorry, it would be rolling down infinitely, but like the hills would be moving with it. So rolling isn't actually a good example. It would just continually, it'd be like being pushed that way, but not like that. So basically it's just like when you jump, you fall down to the earth, but what if the earth just moved as fast as you fell towards it? So you just infinitely pick up speed going down into it. Like that, but you never make contact with the earth, and then there's an anti-earth above you pushing you, and you're like, but they're both moving with you, so you just freaking keep going. Yeah, works. It's clumped together. It's like a trampoline. We've all seen that kind of imagery before. So this is how it would work in two ways. It'd be basically just the forces would be doubled. Technically, you could do all this with just the black hole or the white hole, but this just makes it better, and if you can do it, why not? And I think this would also make it better for objects around the ship, because kind of at that level, if the black hole and white hole are identical but in like opposite ways, objects far away might not feel the effects of the two as harshly, because it's kind of like noise canceling. It's just like, because like in an airplane, it's making that noise and with the noise waves and stuff, and then noise canceling stuff in the headphones play waves that are the exact inverse of that, and that pretty much cancels out the noise entirely, so you don't hear it. It would be like that, but with force from like across the solar system in space. But you know, so we don't die. So in my IA, I just set a few parameters to make it all easier for myself later. Like the mass of the Uwu ship. I set that as just 2 mass of the Saturn V's in the rocket that got to the moon, just because, why not? Yeah, really, that's it. I also wanted to calculate how much time it would take. Well, the main thing that I wanted to do is calculate how long it would take to reach certain speeds and also to reach certain places. And right here, you can see what I calculated. Reaching light speed, how fast it would take for the ship to reach light speed, how fast it would take to reach Proxima Centauri, the nearest star. Analysis on that later, and just to see how long it would take to travel across the entire diameter of the Milky Way, which is pretty big. So, where exactly to place the anomalies? Right here. I decided that the force of gravity that was the weakest was just the best because, you know, why not? I really, yeah, I just set, I set that as another constant for the rest of the paper because I thought it'd be just a good idea to have it out of the way, and I did these tests just to see what kind of forces we were dealing with. Okay, so for the tests, I would really just get the force of the two objects emitted upon the ship, add them together to get the net force. I just did that by plugging things in with the just the normal gravity equation, just the Newtonian one, because I didn't have time to do the other one. And I got this value, and then this value, and just add them together, get this value. And then from that point, as we have the net force, the equation F equals ma can be used because we have the mass of the ship, and we can just ignore the masses of the other two objects because we just assume fancy space technology moves them for us because they're technically being like casted, not really moved. And this allows us with just very simple algebra to get the acceleration from it all. That is just a quick step there. And then we have the acceleration, which is pretty big. So for test 1, it was just the mass of the Earth that we used for each of the thingy, but you know, one of them had the negative mass, which is fine. And that's how we got the acceleration of it all. And then from that point, we can do another one of the big three equations that we learned in AP Physics in order to get t, time. And so okay. So the velocity we want to reach is light speed, so I plug in light speed for final velocity, and then that equals all these other things, and t's in there as well, and we just have to algebra around to get t by itself, and then we produce that. So it's crazy because with this set of circumstances, this ship would reach light speed in 3/thousandths of a second. Freaking insane, right? Okay, and then in order to calculate how much time it would take to reach these other places, we have to use two equations. This new one is another one of the big three, but it has distance instead of time, and everything's just a bit different. It's just a well-known equation as well. And we do all that. We have the distance to Proxima Centauri just based off of research and, you know, looking at it. So from that, we get our final velocity at Proxima Centauri. Because of how the equation works, it gives you velocity squared, and then you just square root velocity, and you're handed your velocity at the end of it all, and then you plug that into the equation that we got that we used to calculate how much time it would take for us to get to light speed. But with the new velocity of that, and then we of course algebra some stuff to get t by itself, and we get that. And this is another thing that kind of shocked me as well, is that with these parameters, with the thing only being 100 meters away, both sides, we could reach Proxima Centauri, the nearest star system, which is 4-ish light years away. in 16 minutes. Or actually, more like 17 minutes, but you know, that's insane. Imagine if we were able to do that. That'd be so cool. We could explore so many places. Of course, we would want to like dial it back before we got there and stuff, so we wouldn't just smash into things and destroy a freaking dwarf star. You know, you don't want to do that. And then I combined those two calculations that happened earlier into one just to make it easier later on, so that we could just plug it all in like here. For when I want to do the Milky Way one, again, I just got the distance value for Milky Way and blah blah blah, and 43 hours it would take. 43 hours for this contraption with only the mass of the Earth on both sides of us, one of them negative, one positive, with our little safety bubble. It would only take 43 hours for us to go all the way across the Milky Way galaxy. It would be a new age of exploration. We could do so much with that. We could get a little. We don't want to get too close to the you know, magnetars and stuff. But I mean, like, we could totally freaking. It'd be so cool. Anyways, yeah, that was test 1, and then test 2, I did just the same stuff again, but instead of the mass of the Earth, I did the mass of the Sun, which would just make acceleration go quicker because, you know, more gravity. So yeah, I got the force of gravity of the Sun, which ended up being this number, and then I got the net force, which ended up being this number, and then I just did everything again to get the acceleration. The acceleration ended up being that, which is, and then to get to light speed again, I just used the same thing, and freaking, okay, this is insane. We would get to light speed that quickly, and then we just keep accelerating. That's insane. Once we get to light speed, we don't just stop accelerating. We keep accelerating, because why not? We can. That's such a thing. It's cool. And then I just used the same equation from again, so we didn't have to, you know, recombine the equation again. So to get to Proxima Centauri, we would get there in 1.73 seconds. Before it was 16 minutes. Now it's less than 2 seconds. That's like teleportation. But then I think it gets even cooler right here, because to get across the entire Milky Way galaxy, it would only take us 4.5 minutes. That's so cool. 4.5 minutes. That, of course, that you would feel the time pass. Yeah, you would, because it's not like kinetic. Okay. Would you feel the time pass? That's actually an interesting question. Would you feel the time pass? Because once... Okay, so, like, when you're falling into a black hole, you obviously accelerate very, very quickly and do this magnification and everything. But from your perspective, everything, as you fall deeper in, 360 degrees around you, not including the black hole, everything that way condenses down into a single point in your vision. You're probably dead by then, but, like, it's really interesting because technically, because of, like, time dilation, stuff like that, once you'd get close to the event horizon of the black hole, time would go by, like, all time would just go, like, for you. You would just see everything. It'd be really weird because if you were an external observer, as the person got closer to the black hole, they would freeze and then redshift away and kind of just dissolve into nothing. But from the person falling into the black hole, you'd basically freeze and you would see the entire lifespan of the universe around you going by in an instant. So from the perspective of the person on the ship, it could actually just seem instantaneous. It could be like, it would relatively to that person, I don't think they would age in that moment out, right? Yeah, no, they wouldn't age. That's interesting. I don't think they, okay, I think my logic is right here, unless it's not, which it could be not, depending on the technologies and stuff, but like with what we know now, that would basically be like a cryogenic pod almost, but not cold. Like you could just have that thing going in a very large loop, and like once it reaches a certain speed, you could turn it off and it would just maintain that speed really, maybe, I don't know. It'd probably be expensive, but I mean, like, wow. I didn't even think of that when writing this thing. No, that's interesting. Like, would that person on the ship sense the time that passed? For them, the time might not even pass. Only to external observers does the time pass, and they see the ship going. That's really cool. That's something to think about. That's really cool. That'd be really weird. Ah. Okay. In conclusion, we went over the introduction, the body, and so we went over kind of why this is cool. I think it's really cool because humans basically wouldn't be able to go extinct because of this. If we inhabited multiple worlds in our solar system, our chances would go down of dying. If we did it across multiple solar systems in the galaxy, our chances would basically be just gone of dying. We'd stick around till the heat death of the universe, and at that point it would be impossible to do anything about it. Probably. Unless technology. No, we're all going to be living inside of some sort of virtual reality soon. That'll be really cool. This stuff is so cool, it gets to me. And so yeah, really, we learned some time values of what goes where and stuff like that. So yeah, the gravity equation I think is really important for all this, because it allowed us to actually get that force, calculate that force, which is really just the catalyst for all the other equations. We wouldn't be able to do that without our acceleration value, and we wouldn't be able to get that without the gravitational force. So I believe that equation is very, very useful, and know it. Yeah, I think, I don't know, it's just so cool. Actually, you don't have to know it, maybe he'll put it on the test. Anyways, yeah, just in conclusion, it's really, really cool. I really like it all. The methods, although they don't involve the Einstein equations, I think they're still pretty reliable. They could be better, but it's high school, whatever. And they're probably going to be pretty accurate as well. Either way. Although, one thing is we don't know how gravity works on really small things and really large scales up close and stuff like that, so I don't know, take all that with a grain of salt, but it's still pretty cool just to kind of see it all, you know? Yeah, just it's really cool. I don't know what else to say. Yeah, like just this whole kind of concept of faster than light travel. It would unlock so many opportunities, so much exploration. Imagine all the cool freaking natural landscapes of alien worlds that we could see. Yeah, yeah.